Anyway, so today we're going to move on to 9.3. And the reason why I can afford just chatting a little bit is you will see 9.3 is trying to find the proper word to describe it. I'll say easy as long as you open to some new concepts. But you will, and also mention that my PM students told me they had matrices before, maybe in Algebra 2, right? And you will see from 9.3, this is why they actually had such a great time with the matrices, like in Algebra 2. And I'm sure that it will be the case for you guys. All right, so still basically simple addition, subtraction, multiplications, right? There's not even divisions. But again, you will have to do these things for a whole bunch of numbers. But guess what? At the end of the day, you're not doing it yourself, right? Use the technology. So today I probably have to do a little bit more talking than I usually do because there's not too much I have to write down. And I pretty much typed up most of the examples except for the last couple of examples I do want to try, with or without calculator, right? So let's get started. So matrix operations. So basically by operations, I mean add, subtract, multiply, or divide, right? But we will have division defined in a strange way for matrices, right? But we're not going to get to division today. So first off, let's take a look at something that we use to describe or to represent, right, a matrix. So a matrix is array, right? If you are used to the coding language, right? So they sometimes just use array in C++, Python, right? Here you have a rectangular array of real numbers with m rows and n columns, right? So we call it a m by n matrix, right? And how many numbers are there in a matrix? Well, it turns out there will be exactly m times n, right? Now, later on, let's not always say they're numbers, right? So we call them elements. Or in this book, they call them entries, okay? Each number, right? Later on, it could be something else, right? You can put your name in it, right? You can put anything you want, right? An object, right? It's just like a space you put in stuff, right? So those stuffs at their location, first row, first column, the top left corner, that little thing is called an entry, okay? But you want to tell people which entry that is, right? Where it is, right? It matters. So you use something like this kind of notation with two subscripts, right? I and j. I and j are integers. They run from 1 to any kind of a big integers you want, right? So 1 to 100. So that means if you're looking at a sub 32, the first index represents the row, and the second index represents the column. So a sub 32 is the entry on the third row. I'm trying to get it right. So third row in the second column. Okay, does that make sense? No? Well, why should it make sense? It's just a way of they describing it, right? Well, give it a try, right? What about this guy? Which row do you think this number 4 is located? The second row, right? Which column? The first column, right? Would you say it's, if you want to use b, lowercase b, b sub 2, 1. 2, 1, 2 stands for the second row, 1 stands for the first column. Row, column, right? M row, n column, right? row, column. That's the order. Now, but when you describe the entire matrix, which includes a lot of entries, right, to a friend, right, or communicate between us, you're going to say, I have a matrix B, right, a matrix A, like the ones you use in the calculator, right? So you have the name for the matrix, which are usually uppercase letters, okay, like A, B, C here, right? Now, when it comes to the entries, they use the corresponding lowercase letter with the double indices, right? It's a convention, right? So you don't have to do that, but at least that when people write something like that, it should make sense to you. So when a matrix A has that many elements, and each element, each entry will be represented by a lowercase a with the index I representing the number of row, the index j representing the number of the column. That's all. Okay. Now, you know that every matrix might look in a bit different, right? When it comes to the size, right? Basically, the number of rows and columns are different. So therefore, you do want to specify the size, the shape of the matrix. Is it a square? Is it like a skinny, like a long matrix? Or is it like a skinny but horizontal, like a strip kind of thing, right? So does it have a lot of rows, right? Does it have a lot more rows than the columns? So you will specify what we call the order of the matrix, right? But the order of the matrix is not telling you what's the total number of entries. Let's say there are 100 entries in it. No, you say the matrix of order 2 by 2. What does it mean that 2 by 2? 2 is telling people there are 2 rows. By 2, the second 2 is the number of columns. So matrix A has an order of 2 by 2. What about the matrix B? The matrix of order, how many rows? 3 rows, 2 columns, so 3 by 2, right? What about C? Order of C is 2 rows, right? 3 columns, so 2 by 3, right? And you do realize that if you swap the row and columns, right, M and N, that will be very different. 3 by 2, 2 by 3, right? So these two matrices look different. Okay. Now, of course, you know there are some special matrices, right, which has the same exact number of rows and columns, and they're called the square matrices. They look square, right? As you can see that letter A is a square matrix. Okay. So far, so good? Just a whole bunch of names. Now, the second bullet point is kind of silly, maybe if you think hard what they're trying to tell you. It's a equality of matrices. It's like, how do you know that 2 matrices are the same? And it's like, I wish I have so this is like if your friend says, hey, what did you get for the quiz? Right? You say, you know, both of us get the same grade. But what? Show me your grade. How do you know that you had the same grade as mine? Right? I didn't even tell you what my grade is. Right? So then you both look up the grade. Right? So you guys both got 100%. So now you know your grades are the same. Right? So you need to see 2 things that you try to compare. Right? So it's like it's easy to say, do you know that 2 and a 2 are the same? Yes, obviously. Right? But here they're saying matrices are not as simple as one single number, but it's number, but it's more than numbers. It's a whole bunch of numbers, right? So this is saying that my class, well, you know what, might have I have exactly 23 students in my AM class, and also exactly 23 students in my PM class. If I say my AM class students have the same grades as my PM classes, it's not it's almost, impossible, right? But if that really happens, that means it's gonna be a student here has the same exact grade as a student in my PM class, okay? But I don't know, maybe we do alphabetical order, right? Whoever has the last grade, started with A, right, has exactly 90%, and the student starts with A in my PM class has exactly 90%, right? So that's what you have to do with the matrix. When you see two matrices, right? So you say they are the same. They need to be the same in every single way, right? Say they have to have the same exact rows, the same exact number of columns. Not to mention every single element or entry must be exactly the same. So basically they are the same, right? They have to look exactly the same. But see that sometimes they can ask you the problems to say, well, A is in terms of X, Y, Z, B is, again, explicit given, 2x2 matrix. They are the same, right? They are equal. But it can only happen if you have X equals 1, Y plus 1 equals 5, Z equals 3, right? And also here, 6 and 6 are equal, right? Every single pair of corresponding elements or entries of the two matrices must be the same, not to mention they must have the same exact order. Exactly the number of rows and exactly the same number of columns, okay? But I hope that it's just, obvious, right? Since you set things, to be the same as each other. Now, why do I have to know that sometimes matrices are the same in a way, right? Because we want to make sure that we can add or subtract them. Because if matrices are a whole bunch of numbers, if you know how to add up or subtract numbers, we should expect something the same for the matrices. But see how straightforward that is. They say add up the two matrices. All you have to do is to just add up the corresponding entries, right? See here, this is A sub 1, 1, right? The top left, A sub 1, 1, the first row, first column will be added to B sub 1, 1, first row, first column. And therefore you get, oh, here, I was looking at this guy, 0, right? And you do the same thing. A sub, now you tell me, A sub what? What are the indices? A sub first row, second column. So A sub 1, 2, right? A sub 1, 2 added to B sub 1, 2, right? And so forth. You add up the corresponding elements. Or if you want to subtract the corresponding elements. But be careful with the sign change, right? So now, question is, are we allowed to add or subtract matrices of different orders? Why not? Okay, that means there are always going to be numbers which are not at the same place anymore. They don't add up, right? So let's say if this guy has an extra column, right? What are you going to do with the third column if the first guy doesn't have a third column, right? So now think about this. Do you have that kind of a, things that you probably don't think that might be a problem, right? So do you ever add up the area of the room to the height of the room? I mean, you could just add the numbers, right? But what does it mean? Area added to the height, right? Or that if you travel, for those who visit Europe, right? That you probably have to use euro, right? Or you have US dollars, you have to convert, right? But some countries that take US dollars. What's the point of add up $100 and 100 pounds, British pounds? It makes no sense, right? They don't add up, right? If you give them, hey, I have $200, and somehow you show up $100 bill, right, and 100 pounds, right? I mean, you say that's $200. I mean, that worth more than $200, right? But you see that things are different kinds, right? Matrices are different kinds because they have different orders. They don't add up or subtract, okay? But anyway, so let's take a break, right? So we'll come back with more concepts and terminology about matrices. But so far, you see that it's fairly straightforward, right? So let's take a 10 minutes break, right? 10 minutes countdown. Right, but if you're kind of bored, feel free to read through the first couple pages of the notes because everything's pretty much typed up, so you can see what you will be getting in the next 50 minutes. Hmm. Um, what are you saying? In the future or only for this time? No, come to my office hour, and because I need to see that you have a device ready to go in every way. Right. All right, let's get started. So as you can see that we will introduce a few more concepts for matrices, but I hope that you will appreciate how similar those terminologies or even their meanings, you know, are compared to the actual numbers, right? So whatever you know, what you can do, what you have been dealing with just pure numbers, right? Even back to, you know, elementary school, we have pretty much the same thing, right? Start with something called the zero matrix. So now, do you recall, you know, when you first, you know, introduce the number zero, you realize that zero means nothing, right? You know, that means if you ever add zero to a number or you subtract zero from another number, it won't make any changes at all, right? And you know what? That happens to matrix. Well, to have a zero matrix, you know what? It's as simple as putting all the zeros, right, for its entries. That's all. You just have a matrix with all entries to be zero. So then you add or even subtract it from another matrix. Then you have, you know, again, the same matrix as before, right? It doesn't change the original matrix. But here's the catch. So there's only one zero in number theory, right? It's the one zero, that's the origin. But there are, technically speaking, infinite many zeros because they are of different orders. You see that? And I can have a matrix that has only one zero in it. Well, first off, is that still a matrix with one row, one column? Well, technically speaking, it is. Because we didn't say that the number of rows and columns for a matrix have to be, you know, more than one. Okay, but that means that we are living in one dimension, right? According to matrices, because we're only dealing with numbers, right? Pure numbers. Doesn't have any row and column indices, right? But that means what you should expect from a lot of the property of matrices, you could sort of guess from what you know about pure numbers, because one row, one column is one-dimensional, like order one matrix. So you can have what we call a column matrix with 3 zeros in it. That's a zero matrix of order 3 by 1, right? And that looks different than a zero row matrix. It has only one row, right, but 3 columns. So basically, they're all zeros, right? And they will be added or subtracted from the corresponding matrix of the same order, right? And do the same thing as the zero matrix in general, right? It will not change the original matrix that you added to or subtracted from. And therefore, the zero matrix is called additive identity. Additive means that you have to add or subtract it, right? Identity means that it doesn't change anything if you add or subtract it from, or you get what I'm saying? It's just, you know, fancy way to say that zero doesn't mean anything if you add or subtract. And there's something called negative matrix. So, but again, you know, thinking about that, if you were thinking about subtracting numbers, right? But I guess that later on you see in mathematics, people like to talk multiplications, right? Rather than divisions. And they'll think of multiplications as more fundamental than divisions. The same thing, obviously, for, you know, addition, subtractions. Addition is more fundamental than subtractions, right? Because you can understand a subtraction between, let's say, A and B are numbers. The subtracting the B from A is equivalent to adding the negative B, right, or adding the opposite of B to the A, right? And it turns out that it works out the same way for matrices. If you subtract the B from A in a matrix way, and you could also do an addition of a negative B, right, added to the A again in a matrix way. Okay. So now, see if you are 100% comfortable with this kind of concept. So I have two matrices, B and a negative B. How much do you think that they add up to? These two are matrices. They add up to be a 0 matrix, right? That means if B are 2 by 2, so 2 rows, 2 columns, right? And they add up to be a 2 by 2 0 matrix. Does it make sense? Now, therefore, I think that there are a lot more reasons for you to believe that negative B is negative. It is a negative number. It is a negative matrix because that's exactly what you expect from a negative thing, right? When you add negative B to the B, what is the number? What is the matrix? It annihilate each other, right? It gets you 0, right? There you go. Not to mention those properties of matrix addition. I say, well, are there any property of a matrix subtractions? No, because subtractions are the special case of addition, right? So look at these. Commutative property, which is a fancy way to say that you can swap the two matrices when you add them, right? A plus B and B plus A are the same. Well, you know that A and B must have the same exact order, right, to be addable. Associative property of addition, that means you can prioritize the order of addition, right? If you add up A and B first, then add the C to them, or add up the B and C, then add the A to them. It's the same thing, okay? Additive identity, saying that there exist 0 matrices. When you add them, right, to matrices, either from the right or the left, it doesn't change that matrix. Additive inverse. Oh, I forgot to mention that. What I mean by additive inverse is that whatever matrix and its negative matrix are called additive inverse of each other, right? Why they're inverse of each other in an addition sense? Because you add them up, you get a 0, right? One is opposite of the other, right? They are inverse of each other, but in the addition sense. Okay, but I hope that you see you don't need to memorize these properties because they just make sense, right? You know what they are. It's just that now you're extending them to matrices. Okay, now multiplications. But I did promise you that we're not going to do multiplications right away, right? We will, but later. But here we do see a multiplication, but trust me that it is not the kind of a fancy, complicated multiplication you have to do for matrices. It's called scalar multiplication. So for those who are learning trig last semester, do you guys know what vectors are? Just remember what that is, right? But what about scalars? What are scalars? Okay, let me give you an example of a scalar in real life. What does it mean, scalar? Say again, vectors magnitude. So yes, scalar is pretty much just the magnitude of a vector. Or let's say scalar is just a number. It's just whatever number you used to, right? You name it, right? Radical 3, 1/2, negative 100, pi, right? So basically, there's no complication about directions. It's just numbers, right? But we have a fancy way to call it scalar. And the reason why they call it scalar is because, you know, what the scalar is going to do to a vector is by rescaling its length, its magnitude, right? But basically, a scalar is just a number. So scalar multiplication is about multiplying a matrix with a pure number, right? A pure scalar. And what it does is it just distributes that scalar. a pure number across the board to make sure that every single entry in the matrix gets multiplied with the same exact number or the same exact scalar. Right? So isn't that straightforward enough? Right? Now take a look. See that this is why I don't even bother to write it up. I have a -5. Right? Now, how do I know that -5 is not a matrix? Edon? That's one way to see it, right? Do you see that? If you have a matrix, you need to have a bracket, right, enclosing a whole bunch of numbers, right? Number 5 or -5 is just by itself, right? Or sometimes you expect maybe a letter, right? Because how could you say, a matrix is as simple as 5, even though that later on you're going to specify more elements, right? So you're going to say, I have a matrix A. You may wonder, so what is matrix A? Hold on a second. Let me show you all the entries in the matrix A, right? Because it's just not one number. So exactly. So -5 right next to the B. You know that the multiplication could be omitted, right? But sometimes you might see a dot, right? But you don't need to. So it means that you are doing what we call a scalar multiplication between a number 5, which is a scalar, a matrix B, right? Matrix B is 2 by 2. So you just go ahead and multiply every single entry in the matrix B with -5, and then you get, the result. It's that simple, right? What about this guy? I have 2 times matrix A, which is a scalar multiplication, 3 times matrix B, then we're going to add them up, right? And you see that the order actually does matter. You do the scalar multiplication before the matrix addition. Again, it's as simple as just PEMDAS, right? Addition goes later, multiplication goes first, even though it's just scalar multiplication. So you multiply every single entry of the A by 2, right? And do that with the B, but multiply every single entry with the 3. Then add up entry by entry, right? There you have it, right? Now, how do you feel if you have a question like that in a test? Do you have to do it as an FRQ? It's not bad, right? Yeah, it's almost like a elementary school math, right? Not to mention, if the numbers gets ugly, that use the calculator, right? But what I'm looking for from those questions. If you were to have an FRQ like that, I need to see if you respect the order of operation, right? Scalar multiplication happens first. Do you realize that you have to add up element by element, entries by entry, right? Or you know what? I might trick you by having 2 matrices of different orders, and you realize they don't add up. Okay. You say it's not edible. It's just like sometimes equations don't have solutions, right? Things don't add up, right? And you see that things don't multiply sometimes, for matrices. All right. Now, again, some properties of scalar multiplications. Now, you know what? I'll let you stare at those properties for maybe a minute to convince yourself that they are still the same as whatever you have expected from multiplications in general. Okay, nothing should surprise you. And by the way, so those lowercase letters are usually, I'm saying usually, scalars, or simply put, pure numbers. Capital letters are matrices. Okay. Now, that 1 is just number 1, right? Scale is a constant, yeah, it's just pure number. So you may know exactly what it is, or you may not know, but you should never overcomplicate it. It's just a number, right? So anyway, so you see that associative property, right? Scalar identity, such a fancy way to say 1. Number 1, right? Scalar identity. Distributive property, right? In 2 different ways. I mean, you get it, right? Either adding up the 2 matrices, then distribute a constant C or a scalar C, or add up the 2 scalars, then distribute the matrix, right? Now, you should be good. Oh, that looks kind of advanced, right? Solving a matrix equation, right? Usually solving equations is, the more advanced topics. Not to mention you have the matrix, right? So let's see how we're going to do that. So we have a X matrix. So it's uppercase. That means, it's a matrix. And usually you use X for maybe unknown, right? So we don't know what the X matrix is. All we know is once you multiply that matrix with 2, which is a scalar multiplication, then you add the matrix A to it, right? And they better, add up to be the matrix B. So given A and B, how would you find what X is? I mean, you see that already typed up, right? But the thing is, what if those X, A, and B are numbers? How would you solve for X? Let's say I have 2x plus A equals B. You see that I'm using lowercase letters, right? That means they aren't numbers. How would you solve for A? How would you solve for X? Right, you subtract A, so you get 2x equals B minus A, right? So now in this case, let's avoid using division. How about that? Let's multiply both sides with a half. And a 2.5, right, cancels, so you have x left over, right? So you have, whatever B minus A with a half, right, will become, right? So you get it, right? That's how easy to solve a numerical or number equation. But now when it comes to matrices, guess what? It works out the same exact way, right? So now when it comes to subtracting the matrix B and matrix A, what do? You do it entry by entry, right? And you know what? A and B must have the same order. Otherwise, they're not subtractable. And the reason why we want people to get used to using multiplication of half or multiplication 1/3, right? Instead of saying dividing by half, dividing by 2, divided by 3 is we haven't defined the division for you. Now I'll let you know ahead of time that the matrix division is not always well defined, right? Which might be a good thing, right? So you don't have to deal with divisions. So now what happens once you find out the matrix subtraction, right? So it works out as a 2x2 matrix with -7, 10, 9, -1. Then you do a scalar multiplication with 1/2. That means all the entries gets multiplied with half, right? And that's how straightforward it is. And now would you say that that could be, a FRQ kind of thing, right? I'm sure that you'll be able to show me all the work, right? Now, matrix multiplication. Notice it's not scalar multiplication, it's matrix multiplication. That means you'll be multiplying matrices. And that's probably the only thing that could still throw people off. But trust me that, it's just about certain rules. And once you get used to it, it will never be an issue. But the only issue is you might forget. So let's first take a look at two matrices. The first matrix has m rows and columns. Second one, n rows and columns. So let me call these two indices inner indices. If I put A and B side by side, A goes first, B goes next, right? These two are inner indices. Now, those two guys are known as outer indices. Here's the first and the most important rule. So you have to remember it because there will be questions asking you about matrix multiplication, right? So the rule is the matrices can only multiply with each other if the inner indices are the same. You might say, what if they're different? Well, they don't multiply. It's not allowed. If you ever do that, either computer, calculator, right, or people will complain. Okay? Or a fancy way to say it is two matrices are not compatible. right, for multiplication. They're not compatible. That means the two inner indices are not the same. Okay. But what would you get once you multiply a matrix of n by n, right, and another matrix n by, sorry, p, right? So that's now this is why we need to identify the order of the two matrices when it comes to multiplication. Which one goes first? It's the matrix A goes first, right? And also I need to identify the inner and outer indices. So it turns out that the two inner indices, since they're the same, right, they got contracted. When I say contract, that means they're gone. They're eaten up, right? For some reason, they're not there anymore. What you're left with, once you multiply the matrix A and B, you'll get a new matrix of order M by P. So there will be M rows, P columns. You see that the outer indices survive. Okay. Now, very quick. A matrix A, IJ. Sometimes you might see people putting down 3 times 2 at the bottom right corner, right next to the square bracket. That's for them to tell you what the order of the matrix is. So 2 by 3, that means how many rows? 2 rows, right? Columns, 3 columns, right? So if that matrix, so I do put a star to let you know it's a multiplication. You don't have to, right? So you're multiplying that with a matrix B sub ij, right? 3 by 4. Now, once you multiply these two matrices, so you're gonna get a, let's say, a C matrix ij. Don't worry about the ij. I'm just using that as a notation. Can you guys predict the order of the C matrix? What will be the order? How many rows and columns would that be in matrix C? Rebecca? 6 by 3. Now, take a close look. Those two are inner indices, right? They are gone. What indices survive? The outer indices. So it will be 2 by 4. Okay. Now, you should remember that. That's the first and the most important conclusion about matrix multiplication. And don't ask me why, because there's no reason why that's how they define it. Okay. But what if I swap those two guys? Okay. Let me zoom out a little bit. What if I have B ij and it's 3 by 4, right? Times aij, that's 2 by 3. What do you say? Do they multiply? According to the rule, the inner indices must be the same, but they're not, right? So now, however you want to put it, maybe undefined, right? Or D and E does not exist, right? Or not gonna work, right? Whatever you want to say, right? Not compatible. They don't multiply. Just tell me that. And of course, I might not want to have a question like that, for 5 points. You never know. I might just put it out there and make it so complicated, and you realize, at the end of the day, I don't have to do anything because it's a trick question, right? All right. So that's the first thing. and the most important thing. The second thing you have to do to be able to actually calculate what the matrix multiplication is to seriously remember how to do it, right? So first is when and whether you can do it, right? When you do it or whether you can do it depends on the inner indices, right? If the two matrices pass the test, right? The indices, indices are the same, so now you can multiply them. But the question is how, right? So this might be a bit too abstract, but again, bear with me for a second. So the matrix A has, certain number of rows and columns, right? But I'm gonna take the ith row. Oh, it's right there, right? The ith row of A, and I'll somehow, quote unquote, multiply that with the jth column of the B. So the first matrix, I take the row. The second matrix, I take the column, right? But it's the ith row in the jth column. But how do you multiply them? Let's say this is A sub, now let's say there are only 3 columns, right? This is, and let's say maybe, let's go with maybe a second row. Let's say second row. So this is A sub 2, 1, right? What does the 2, 1 means? Second row, first column, right? A sub 2, 2, A sub 2, 3. Make sense? Okay. Now, the jth column, right? Let's say maybe the third column. So now that's going to be B sub 1, 3, B sub 2, 3, B sub 3, 3, right? Make sense? The first row, but the third column, second row, third column, third row, third column, right? So what you're going to multiply, what you're going to do by multiplying the second row and third column is you do A sub 2, 1 times B sub 1, 3 plus A sub 2, 2 times B sub 2, 3 plus A sub 2, 3 times B sub 3, 3, right? And what you're going to get is that new matrix, right? And I guess that they call it P, right? You know what? That is P. Guess which element of P is? It will be the second row, third column. All right, now you multiply matrices. What you get will be still a matrix. The matrix has many entries, right? Basically, we want to find out every single entry of the product of the two matrices. The way to get it is, let's say if you want the second row, the third column after you multiply. What you're going to go is you're going to go to the matrix A and take the second row. Go to matrix B and get the third column. Multiply the second row of A with the third row of column. And what you're going to get by doing this kind of a weird way of a multiplication and addition, you're going to get the entry on the second row and the third column of the new matrix. Now, are you able to remember that? Now I ask you to make sense of it, right? It's just a rule, right? Now, how about we try that? All right, so let's try to do it, right, all together, right? And I'm sure you will get it. Okay, so now letter A on whichever page. So let's do A times B. Matrix A times matrix B. First off, are they compatible? Can A and B multiply? What's the order of A? 2 rows, 2 columns, right? What about order of the B? 2 rows, 3 columns. Do they multiply? Yes, right? See that? The inner indices are the same. But once you multiply them, what will be the order of the new matrix once you've done it? How many rows and columns are you expecting at the end? 2 by 2 times 2 by 3. The outer indices survive. So you're expecting 2 rows and 3 columns. Okay? Now, 2, 1, 3, negative 5, right? Times 4, 1, 3, negative 2, 6, 3. Okay? So I need a matrix that has 6 entries, right? Because there are 2 rows, right? 3 columns. So now you don't have to do that, but I'll put in some divider. To let you know that I need to work on all 6 entries, right? Starting from the first one. Which entry is that? Which row, which column? It's the first row, first column, right? That means you should get the first row from matrix A, first column of matrix B, right? Let me highlight them. You don't have to. I'm just doing it for you, right? So first row, first column, right? So then what you do is you multiply the corresponding element or entries. What you do is 2 times 4. Oops. Plus 3 times 1. And what do you get? 11, right? So first row, first column of the matrix, once you multiply A and B, it will be 11. You get that? Right? Well, maybe just try it one more. So what about the second column? First row, second column. I need the first row, right? But now the second column, right? So then we do that. Can you guys figure out the mental math? First row times the second column, what do I get? 2 times 3 plus 3 times negative 2. What do you get? Oh, say it again. Why is that negative 36? That's why, exactly. So that's why we make mistakes as humans, because, you might not see it, clearly, right? It is 0, right? Because 2 times 3 is 6, 3 times negative 2 is negative 6, added to be 0, right? So now, go ahead and fill out the remaining entries. I need to have all these entries figured out. All right, go ahead. Not that bad, right? 20. Check the math. Basically, those three entries. Yeah. Well, so let's see here. That's the first row, third column, right? First row, third column. So it's 2 times 6, which is 12. And 3 times 3 is 9.
Oh, sorry.
Right. No, that's...
I wasn't under the impression and then
yeah, it's row by column. Yeah, it's very non-intuitive, and that's why people and we making mistakes. And sometimes, you know, you can help it. All right. Anyway, take a look. So now for a network like that, I will say you will better off to get it right for the first trial. I'm not saying that you have to, because it will be frustrating if you go back and forth and check it, right? So basically, just every time you try to work on an entry, right, just be careful, right? Ask yourself, which element is that, right? Or let's say this guy. You say, well, that's the second row, second column, right? So then you go take the second row, the first guy, second column, the second guy, multiply. But if I were you, I'll actually, you know, maybe use your finger to point at the numbers to make sure that you're multiplying the same, the things corresponding, right? It'll be this guy, multiply that, right? 1 times 3. Then remember it or write it down. Then -5 times 2, -10. 3 plus -10. Wait, did I? I'm sorry, there's a typo there. B has a -2. So it's 3 plus, so 1 times 3 is 3, right? -5 times -2 is 10. So it has to be 13, right? Now, do you see that? It might not be your math. It might be you write down something wrong, right? But that's also going to be hard for me. You know, when I see that, wait, how come that things are close but not exactly the same? I have to go back and see, and then realize, oh, the student put down the wrong number in the first place, right? Which could very likely happen. So now, what about B times A? Don't do it until you realize that you could do it, right? Because they might not be compatible, right? So don't dive into the math. Ask yourself, what's the order of the B? 2 by 3, right? What's the order of the A? 2 by 2. So it's a matrix with 2 by 3, right? Times a matrix with the order 2 by 2. They don't multiply. So tell me that. DNE or whatever you want. All right. Now, again, any questions so far? Okay. Now, look at those matrices. A, B, and C, right? So you want to do A times B or A times C, then plus B squared. Well, what does it mean, B squared? I didn't teach you how to square the matrix. So you will multiply the B with itself. So B squared is nothing but B times B. Right? So again, it's still matrix multiplication. Okay. Now, and you have, you know, AB, right? A times C plus C squared, right? So what if I ask you to do that in test? You know, even though they're still simple numbers, right? Some of them are negative, right? But that will be tedious, right? And, you know, I'm not surprised that people is going to get a lot of errors, right? And therefore, you better use calculator. Right? So now let's give it a try. All right, so take out your calculator. So what I want to do is in the next minute or two, see how fast you guys can be. I want you to type up in your calculator. Go to second matrix. You see I have done the 3 matrix already, right? Ahead of the time. So go put in matrix A, B, and C the same exact way that I told you on that packet. Go ahead and type it up, right? And you know that you should be fast, right? So A is 2 by 3, right? B is 3 by 2. C is 2 by 2. Go ahead and type up all 3 matrices. All right. So I think that should be good enough, right? But if you didn't finish typing up, that's fine, because you know what to do, right? I just want you to have something to play with. So very important. So I noticed that, you might not realize sometimes you want to exit out, then start to play with them, right? So once you edit them, right? So go second, quit. So now you know that the calculator has everything stored, right? So if you want to call on matrix A, right? Don't type in. People saw that, oh, there's a square bracket here, and there's a letter A. Let me type in square bracket A, square bracket. It's not going to work. You have to go through second matrix and call on it, right? So let's say type in 1, hit enter, right? It says, you know what, that's what you typed in. If you want, can do a sanity check to see if you typed in correctly, right? So now what do we want to do for the first computation? So it's A times B, right? Let's go ahead and call A. Second matrix, right? A. So multiply with the B, right? Let's just do multiplication, right? It's just multiplication sign, right? It's the start. Then you call it the B. A times B, right? Hit enter, and it's done. Okay. Now let's try the second one. A times C plus B squared, right? So let's call it on A, okay, times C, which I know is number 3. All right, so second matrix 3. A times C, right? Don't enter at this point. Keep typing, right? Plus B squared, right? Oh, so you thought that you have to type in B times B? No. Calculator is smart enough. If you do B and do the square, right? You see the square there? X squared. Square it. Hit enter. Oh, what does it say? Dimension mismatch. Dimensions are another way to say the order of the matrices. The rows and columns don't match. So now let's go back to see what's wrong with the matrices. First off, A and C. What's the order of A? Rows and columns. 2 by 3, right? The order of B, 3 by 2. Do they multiply? Yes, we did that, right, already, right? So now, what about a B? 3 by 2, right? Does B multiply with itself? If 3 by 2 times 3 by 2, it doesn't match, right? So for some reason that B doesn't even like itself, right? It doesn't even multiply with itself. So that's something that's not as intuitive as numbers, right? So there's something wrong with it. So now let's just do one last, calculation real quick. So AB right, plus c squared. Where is it? Okay, here, right? Right, so let's ignore that. So let's do a times b, right, plus c squared. All right, so let's go with second matrix c, right, square. There you go. Okay, that's how easy it is. So now you know that there will be definitely matrix questions on the test. So at this point, you guys should be able to work with, of course, you know, the homework 9.3, because I did finish everything for 9.3. And you should work all the way to question, I think a lot of them, right? 27, thank you. So question 27 on chapter 9, review packet. All right, not for a quiz, but for the test next Wednesday, all right?